Hello everyone, your Dr. Ziatahir here. This video tutorial is solution to problem 8.30a of chapter 8 continuous system from mechanical vibration 6th edition by S.S. Rao. So that is 8.30 from chapter 8 continuous system. So the problem description is compute first three natural frequencies and the corresponding mode shape of the transverse vibration of a uniform beam of rectangular cross section 100 times 300 millimeter. So here width is 100 and depth is 300 with length equal to meter, modulus of elasticity as 20.5 into 10 to the raised by 10 Newton per meter square. Density is 7.83 into 10 to the raised by 3 kilogram per meter square for the beam when both ends are simply supported. So it's mean that we need to calculate natural frequency and mode shape of a simply supported beam. So this uh, is problem 8.3 from chapter 8 of this mechanical vibration by S.S. Rao. So now objective is to find first three natural frequencies and to plot first three mode shapes. So equation used for is a natural frequency, which is equation 8.93 from chapter 8 of the book. Omega is equal to beta square radical EI rho A, or otherwise beta L square EI radical rho A L squared. So E is modulus of velocity, I is that is second moment of area of the cross section. A is the area of cross section, rho is density, L is length of the beam, and beta here is we need to calculate. And for that frequency equation, so this beta is calculated from frequency equation, so which is sine beta n L equal to 0. This is from figure 8.515 of the book. So this is for when both ends are simple support, and then mode shape or normal function. So Wnx is equal to Cn sine beta nx. So to find mode shape, first we need to find that sine beta nx. And this is also taken from figure 8.15 of chapter 8. So how to tackle this one? So first we need to solve frequency equation for first three modes. So first to solve frequency equation for first three modes, once uh, by solving frequency equation, we will get its root in terms of beta L. So once first three roots of beta L, this equation are computed, then need to substitute in this equation, or once you have beta L, so divide it by length to get beta. So both of these equations can be used. So once we have beta, so then it can be plotted. More shape can be plotted. So where x is from 0 to L. So uh, I'm going to solve this in MATLAB, and the function used in MATLAB are VPA solve function, then double function, and then plot function. So these functions I am going to use. To solve this problem, the first is need to solve frequency equation. And the solution of frequency equation can be found, it is available in figure 8.15, like as here. So that is the frequency equation, and that is the solution of frequency equation for first four roots. So to for solution of frequency equation, I have recorded these two videos. So like as mechanical vibration, example 8.17, that is solution of frequency equation for single root, or then solution of frequency equation for five roots. So how to solve that in MATLAB, I have explained in both of these two videos in my channel, and the playlist is mechanical vibration solutions. I am using MATLAB in standard layout. There's a default layout, and I'm going to use, there are two options. Either you can go for new script, but I'm going for live script. So that is a new live script, and I'm going to save that as I'm going 8 point problem 8.30a. Okay, so it doesn't let me that. So MATLAB doesn't allow spaces or dots, so you need to use that underscore for it. So start with double percentage sign problem 8.30a and press enter. So it will give a heading problem 83a, and that is only possible in live script. And then I'm going to name it as. So that is a heading problem 8.30a natural frequency and more shapes of simply supported being. So the first part is to find to solve the frequency equation. The first step is solve frequency equation. And for solve frequency equation, as I described before, so I am using the script which I have developed here in this problem. So to solve frequency equation, I'm using SYMS. So that is equations in symbolic form, and the variable is BL because here the variable is beta L. So it's BL here, and equation is sine beta L equal to 0. So that is the equation which is required, and here I am using VPA solve function. So that VPA solve function, what it does, it take an equation and find a variable for initial range. So here initial range is I to j, and then uh, I is from 1 to 10 and j is the next value. So I have here initiated empty matrix BLI. So it will fill that in BLI and try to and create a solution. So let's say I am going to run that part of script, and then here you can see, so the first three roots are between 1 to 10. So these are the three values of BLI: 3.146, which is pi, then 2 pi, and 3 pi. So these are the value pi, 2 pi, and 3 pi there. So that first part is done to solve frequency equation. Now the next step is first objective to find first three natural frequencies, and for these three natural frequencies now we have these three values of beta L, and we need EI, rho, A, and L. So most of the values are here. So I is BD cubed over 12, and A is length into width. So now I am going to solve that one, and first we need to get beam details or beam properties, and then further to find natural frequency. So next step, next heading is beam properties. Okay, and I'm going to add all these beam dimensions and then calculation. So now L is the length of the beam, B is the width of the beam, which is 100 millimeter. D is the depth of the beam, which is 300. E is the Poisson ratio 20. E is the modulus of elasticity 20.5 into 10 to the power 10 in Newton per meter square. And rho is the density 7.83 into 10 to the power 3. And then I calculated A and I from here. So all these properties, they are given here. So now these are the beam properties. So next I need to find natural frequencies. So the natural frequencies, that is the next heading. And for natural frequency, the formula is omega n is equal to beta L squared into EI rho A L raised by 4. So the natural frequency in radian per second, so that is omega n is equal to BLI squared into square root EI rho A L raised by 4. And then natural frequency in hertz, that is Fn. So that omega n over 2 pi. So then I'll get that omega n, three values of omega n. So these are the three values of omega n. So it is 1093.4, 4373.5, 9840.3. So these are three frequencies in radians per second. So these are the answers for this 8.30 part A. So the answers which are here. So I got the same answers here. Now the last step is to plot first three mode shapes. And to plot first three mode shapes, the formula is omega n Cn, and that Cn is taken as 1, and sine beta x, and this x is from 0 to L. So I'm going to solve it. I'm going to use that plot function for it, and then I'm going to write a small script for this function. So it take values of beta L, it take values of beta L, and then it plot that mod shape. So the next heading is mod shape. So that is the mod shape, and I'm going to write a function right there. So the function will go end of the script. So if you are using going to write a function in a script and then you want to execute that in the function again. So now the name of function I have here mod shape, okay, and then what is it is doing? It is taking value of BL, okay. So once it take the value of BL and it take length and then dx. So dx is like the delta x and how you are going to, which interval you are going to use. So what it's going to do, it is going to calculate b from dividing bl by l, and then x, it's going to divide that x length from 0 to L with the interval dx, and then W is sine into bx. So that is the formula. So sine x, I'm using that Cn x as. So C as 1, so W is equal to Cn into sine bx. So that is the function I have written. And now I'm going to execute that function for first, second, and third mode shapes. So that is, first I'm going to plot base state. So base state, I have given interval here as 0.01. So x is, it is going to divide L, uh, so L into 0 to L with that interval, and W 0 is zeros because uh, when we have that base state, so in the base state, the function mod shape will be, all values of that will be 0, and then what it will do, it will plot that and then hold on. So I am using a black color with a dash line to plot base state. So that is now for the base state, x label is length in meters and normal function wx, so that is base state is being plotted here. Then there is a first mode, and for the first mode I am using that BL1. So because this BL is here you can see it contains values of beta L. So I'm giving that as input, and then dx, which I have already defined, is 0.01 and L is 2. And I'm going to plot x versus W1. This is the first mode with the blue color. So I've just copied that first mode to the second mode. So BL is BLI and the second value of that vector, and then it's plot W2, and then similarly the third mode, and then it's going to plot that as green. So first mode as blue, second mode as red, and the third mode as blue. So now these are the three mode shapes. The blue one is the first one, red is the second one, and then green is the third one. So, so these are the, so these are three mode shapes, first, second, and third. So I have added the legends for them. Here you can see that I have added the legend, and then in the figure here, so I can view and then plot browser. So that is a base state. Then that is the first mode along with base state. Then that is the second mode along with base state. And then that is the third mode along with base state. So these are the three modes. So that whole problem is solved. Thank you very much for watching. I hope that you find this video helpful.